Welcome friends and families. Please hydrate yourself with water. Okay. So a few days ago, one of my friends suddenly asked me, Badhon, do you know how many elements are there in our universe? I was like, yes, I know. It's 118 elements in our universe. I was like, yeah, you should know that. And then he told me that, yeah, you are right. But do you know how you got the elements? I was like, I know a little bit about it. Like I know it's from stars. It's from we got our solar system or Earth from the explosion of the stars. Like we call it supernova or something like that. It was like, yes, you are like partially right. We we are actually the remnants of the stars. We are from the star explosions. Yes, you are right. But how like the stars create like from hydrogen to helium for and so on, like carbon, oxygen, so up to like iron. It creates up to iron. I was like, why it creates to iron? Like after that, doesn't it create anything? He was like, yeah, the the sun actually produces up to iron, and beyond that it can produce. I was like, why? He told me that maybe I'll tell you some other day, but today's topic is we're gonna stick to the how we got the elements in our universe. Okay, then he told me that how we got in this, like how we can get bigger and bigger atoms. I was like, maybe through nuclear fusions. In our sun we get from hydrogen to helium through nuclear fusions. He was like, yeah, you're right, you're actually right. We get the bigger elements from nuclear fusion reactions. So can you explain what happens in our sun? I was like, yeah, maybe I can explain. Like two hydrogen atoms will like collide and they make helium. Like he was like, actually you are partially right. Actually, two hydrogen atoms at first create a isotope of hydrogen, deuterium, and then it goes up to like a isotope of beryllium and then reverts back to helium. But you are partially right that for helium to produce, we need two hydrogen atoms to be in a single atom. Like made like two in like if we take two hydrogen atoms, like both have a proton, two protons, and two protons must be in a single nucleus for this fusion to happen. I was like, yes, maybe the sun does that thing. He was like, yes, the sun does that thing, but do you know one thing, like if for this to happen, we know from Coulomb's force, two same type of charge, in this case two positive charge repulse each other. So for them to be in a single nucleus or for them to be in a strong nuclear force, it needs to go through this barrier. It needs to cross the potential barrier due to the Coulomb force. I was like, yes, maybe it does. Maybe through some other forces, some other energy sources it does. It was like, what are the energy sources? Maybe like I was like, the temperature of the sun is very high, like some in millions of degrees. Maybe the temperature makes up for the kinetic energy for the nucleus, and the kinetic energy is maybe way more than the potential barrier or the Coulomb force or Coulomb barrier, and it crosses the barrier and makes the atom. It was like, actually no. If you think about our sun, like how we get the kinetic energy for the proton from the thermal energy, from the temperature of the sun. Yes, then like from where we get the temperature? our sun is almost 87% hydrogen and 10 to 11% helium. So due to the gravitational potential energy converting to thermal energy, we got massive amount of temperature like 10 to 15 million degree Celsius or Kelvin. And that because of the temperature, because of this thermal energy, the hydrogen gets, the nucleus of the hydrogen gets kinetic energy, and if the kinetic energy is more than the potential barrier, it may cross the barrier and make helium. Yes, but do you know the thing that the temperature of our sun is not enough for this to happen, is not enough for it to provide enough kinetic energy to cross the barrier. I was like, what? Yes, my friend, he told me that the temperature needed for our sun to fuse from hydrogen to helium is in billion degrees Celsius, it at least a billion degrees Celsius, but the core of our sun is, we know that 10 to 15 million degrees Celsius. It's way less than needed. So actually, like if you think about in our classical physics knowledge, it is not possible to go beyond the barrier. It is not possible to go through this wall without breaking or doing something with the wall. It is not possible for us to go through the wall and not break it. And if we think it for the hydrogen and helium, it's not possible for the helium to make. But still we get nuclear fusion in our sun. How? I was like, maybe some other energy sources that like provides the enough energy. I was like, no, there is no other sources like that provides enough energy for this fusion to start. So how we get the fusion then? Like if it doesn't have enough energy to start the fusion, and if it doesn't have other sources to provide the energy, then how we get from hydrogen to helium, or in other stars carbon, oxygen, other bigger and bigger elements? It was like classic in our knowledge of classical physics, we cannot explain it. To explain it, we need to understand quantum mechanics, and specifically quantum tunneling. There is a term called quantum tunneling. Okay, then through quantum tunneling we can explain this. I was like, okay, like, can you explain it a little bit? I was like, okay, like, do you know the Schrodinger equation for a wave function, Schrodinger time dependent and Schrodinger time independent equation? I was like, yeah, I heard of these equations. Yes, I kind of know that. It was like, in this equation, for smaller and smaller particles, we can think it as wave function. It is not a wave, but it behaves like a wave function. And for a wave to be anywhere in the universe, the probability is not zero. In classically, we can say that the particle to cross the barrier is zero, but quantum mechanics says that if we think the particle as a wave function, in this case the nucleus or the proton, then the probability to find it anywhere is not zero, because the potential barrier is not infinity. It's not infinity potential or something. So we can get a non-zero probability to go through the barrier. So what is the probability for our sun? It's 10 to the power minus 20 or something magnitude. Way low. Like for every 10 to the power 20 particles, maybe one particle can go through the barrier. I was like, I don't get it, man. Like, how can something go through a barrier that is not possible to go through. Like, it's not possible, but how can we do that? Because like this is the thing for quantum mechanics. You cannot think it like with the knowledge of classical physics. I was like, okay, then explain it a little bit more. It was like, if we solve the time independent equation from Schrodinger, like Schrodinger time independent equation, then we can get that for the amplitude of the wave function to cross the barrier, the probability, the proportion of the amplitude to cross the barrier and like to not cross the barrier, the proportion density is not, the proportion square is not 0, and the proportion square is represents the probability density, and it's not 0, it's in 10 to the power minus 20 magnitude. And for this we get some particles that go through the barrier, and we get quantum tunneling and we get nuclear fusion. And this is also the reason the sun doesn't burn all his energy at once. Like if the quantum tunneling didn't happen, and if the particle or if the proton had enough energy to go to the barrier, then maybe all the hydrogen instantly become helium, and the nuclear fission would have stopped, and we wouldn't have get the solar system, and we wouldn't exist. Because of the quantum tunneling, the universe can sustain, the solar system can sustain, the stars can sustain. And do you know the fun part is, the bigger the star is, the less and the less lifetime it gets because of this. Because the bigger stars have more temperature in their core, and the more the temperature is, the more the kinetic energy, and the more the energy is, the more the tunneling probability. And because that if the tunneling probability increases, the lifetime of the star gets lower and lower and lower. And thankfully our sun is not that big for like the lifetime. Maybe it may stay some billions of years more, our sun. So it's burning, but it's burning slowly, because the number of atoms in our sun is like in 10 to the power 57 magnitude. It's way more than the rate it is burning in. So we don't have to worry about our sun burning only its energy. So in our lifetime it wouldn't happen. So the thing is, due to the quantum tunneling, even though our sun doesn't have enough temperature to start nuclear fusion, it does. Now I ask him, so if the sun doesn't have enough temperature for the fusion to start, and it does do fusion, then why don't our Earth doesn't do nuclear fusion? Why don't our Earth's core doesn't do? It was like, that's a nice question, but think about it. The core of our Earth is not that hot, or the number of particles in our Earth is not that high. It's way less than the sun. So if you think about the probability and the number of particles, the probability is way lower than the number of particles. So like if we think realistically, the probability is actually 0. Like if you think about it, the number of particles is lower than the probability, so we can say it as 0. So it doesn't happen in our Earth. But the bigger the star is, the probability is way more, and the quantum tunneling can happen way and way often. Okay, so this is why our universe and we all exist, because of this thing called quantum tunneling. And I asked him, can you actually explain it mathematically? He was like, yeah, if you want that, I will explain it mathematically. Next time we see. I was like, yes, I'll wait for that day to like line it mathematically and to actually see how the probability comes, like how we get the probability actual value for our sum. It was like, okay, I'll tell you the next day we meet. Till then, thank you for listening to me and always stay hydrated, guys. Thank you.